Welcome back to the video course on fluid mechanics. Today's lecture we will see a new chapter, boundary layer theory and applications. So, in this the important objectives of this lecture or the different topics which we will discussing are: first one is external flows and boundary layer, and then we will discuss the various concepts of boundary layer, and then we will be discussing the laminar and turbulent boundary layer and related theory, and then we will be discussing specifically on the boundary layer over flat plate, and then boundary layer in pipe flow, and then we will be discussing various topics on flow separation. Then also we will be discussing various topics like drag and lift on immersed bodies, and then we will be discussing on the circulation. So, as say we discussed earlier in some of the other lectures, so this boundary layer is one of the most important subject in fluid mechanics, since say the flow, as we have discussed earlier, can be classified into external flows and internal flows. So, many times say the fluid is passing through, most of the time the fluid is passing through either just in a pipe, like in the case of internal flows, or it is passing through our body over different kinds of bodies, or it is passing through a channel like in an open channel flow. So, all these places we can see that say the fluid is, it is some part of say at the bottom or on the sides of the container through which the fluid is passing, then there is always the fluid is touching the solid boundary. So, the fluid is moving and the solid boundary, most of the time it is at so it may not be moving, sometimes it may be moving. So, there will be always a velocity difference. If it is not moving, the solid is not moving, then the velocity of the container or the over which the fluid is moving, that is the velocity 0, and then fluid has got a velocity. And say sometimes like in the case of a moving vehicle, a car or a bus or a flying machine like a airplane or a space shuttle, then the body itself is moving, and then also the fluid may not be moving, but sometimes the fluid also may be moving. So, in all these aspects you can see that there is always say some way of interaction between fluid and structure interaction, or solid body interaction, fluid and solid body interaction. So, you can see here, say when a car is moving here, you can see that and it is passing through the air, or there is wind also, then you can see that if you analyze the flow passing over it, you can see the various phenomenon like this. So, initially a boundary layer is created, and then also the flow is transforming from laminar to turbulent. Or if you consider the flow passes through flow over an circular cylinder or a sphere, you can see how the system is working. So, there is always, due to, since the cylinder here it is not moving, it is on the periphery, you can see that fluid due to the viscous forces, you can see that there is a no slip condition. So, this flow past immersed bodies, as we have seen here, or all these cases, many field problems, you can see that there is always no slip condition, and then fluid flow can be classified as external flow and internal flow. Like here this is external flow, that means the flow over a just like a block like this here, or you can see that this a bird is flying bird, you can see that here the bird is moving and then the fluid is surrounding it. So, here we can see that all these cases are external flow problems, or the fluid flow surrounding an airplane or a space shuttle or a submarine. All these cases are external flows. But then here you can see that the solid or the body which is considering is, it is like this, and fluid is surrounding it. So, that is called external flow or flow past objects or immersed bodies. So, there are a number of examples, as I mentioned, airplane, like in the aerodynamics of flow past vehicles, buildings, etc. So, here the important parameter is the shape of the body. So, depending upon the shape of the body, the flow behavior changes, and then we have to analyze depending upon the shape of the body, whether it is a blunt body, it is a smooth body, or whether it is a streamlined body. Depending upon that, the flow behaves differently. So, external flows are important class of fluid flow problems which we have to deal most of the time, and then In this case, you can see that, as you can see here, the flow surrounding a fluid flow surrounding a bird, you can see that here there is a boundary layer is created. So, and also here you can see in this typical case, say whenever the flow is taking place over the block, then you can see that the fluid flow will be coming like this, and then this solid is always at it is not moving. So, there is a no slip condition here and a boundary layer is created. So, like this, most of the external flows problems, there is always a boundary layer created, and then we have to deal with respect to this boundary layer. When we analyze the fluid flow, we have to deal with this boundary layer, and then the fluid flow on the remaining fluid flow. Some days other than the boundary layer, we can consider as a just like in the potential flow or ideal flow. And then also in the case of internal flows, other class of the flow is internal flow, where the fluid flowing is contained in a solid media or in a container, like in the case of pipe. You can see here this is a pipe flow. Then you can see that the say from here the flow starts, and then it is as the flow progresses, you can see that since here on the sides of the pipe, here on this side and this side, you can see it is no slip boundary condition, and then fluid is say with respect to this, there is velocity changes taking place, and then this also boundary layer is created for the internal flows also. So, like this, there can be number of examples where we can show that this say wherever the fluid may be flowing through an internal, if it's like an internal flow in the case of pipe flow, or the fluid passing over immersed bodies or past objects, then external flow, all these cases a boundary layer are created, and then we have to deal in most of the practical fluid flow problems this boundary layer. Like this, always this boundary layer is major area which we have to study in detail, how the boundary layer is behaving, whether it is laminar, turbulent, and then how the velocity changes, how the pressure and other parameters changes in the boundary layer. Since this is say most of the say aerodynamics, like a flying vehicle, airplane, or space shuttle. So, this analysis, the boundary layer analysis, is very important, since based upon that only we can design this airplane or the space shuttle, since this velocity variation is very important. But outside the boundary layer, we can approximate, and depending upon the flow condition, we can even consider it as a potential flow. So, this concept of boundary layer is say first we will discuss, and then we will see some of the equations related to the boundary layer. So, as we have already seen in many of the cases, wherever viscous flow is there, so you can see that there is a no slip condition at the boundary, and then say the fluid is flowing, and then when due to this no slip condition at the boundary, and then the flowing fluid has a velocity, then this velocity of flow at the solid boundary should be same as that of the boundary. Due to this condition and the viscous effect, a thin layer near to the boundary layer is generated. So, you can see that even in this case also, this figure also, you can see that the thin layer here is generated, and this is called the boundary layer. So, whenever we deal with the viscous flow, this boundary layer, due to the no slip condition, boundary layer is all the times we have to deal with the boundary layer. So, this theory of the boundary layer is actually the backbone of the modern fluid dynamics. So, you can see that this the boundary layer theory has been proposed in the beginning of 20th century by Prandtl and other scientists, and then many theories were developed related to the boundary layer, and since we could say distinguish the boundary layer, and then say we could derive some expression for the velocity and pressure variation boundary layer. Due to this development in the boundary layer and the modern fluid dynamics only, most of these say flying vehicles like airplane or space shuttle, all these developments took place in the 20th century. So, before going more details on the boundary layer, I just want to show a few seconds of video taken from the video produced by Handhaus, which is available in the internet. So, here you can see how a boundary layer is generated. Say a flow is going like this, and then if a solid is placed like this, then you can see that how a boundary layer is generated and how the velocity distribution takes place, and then how the separation takes place. So, related to this, further we will be discussing all these phenomena in detail, and then we will be trying to derive expression for this boundary layer aspects later. So, now as I mentioned, so as we have already seen here, this boundary layer is very important phenomena which we have to consider. So, and since we can say differentiate whenever the fluid flow is taking place, especially in the case of an immersed body or a flow past a body, then we can, if we can take the consider the boundary layer, then the flow outside the boundary layer can be considered as a potential flow or ideal flow. So, you can see here in this slide, say if this is up to the boundary layer which we consider when we deal with viscous fluid. So, if you plot the velocity profile for real and ideal fluid flow, so real fluid you can see that due to the no slip condition here, the velocity distribution will be going parabolically like this, and then say depending upon the flow depth it is coming to here the maximum. But in the case of ideal fluid, we do not have to consider this no slip condition. So, it is the fluid velocity will be like this. So, if you can identify the exact location of the boundary layer, and then say you can see that after that we can consider, even we can approximate, even though it is not may not be 100% accurate approximation, but say we can approximate many times after this boundary layer we can consider as an ideal fluid flow or a potential flow, that so that we can confine, we can reduce the boundary of the problem, and then we can deal with the problem much easier in comparison with when we consider throughout the complete domain, where the flow over an airplane or the flow over a space shuttle. When we consider, then we have to go for a large domain for analysis. But if this boundary layer can be identified, and then say up to that we have to deal very precisely, and then after beyond the boundary layer we can either consider as an ideal fluid for potential flows, so that we get a very simplified relation to solve the problem. So, when we consider the boundary layer, so this kinds of separation always helps to get a better solution. So, now we will further discuss various fundamental definitions as far as boundary layer is concerned. So, here we say, as we have already discussed, the differences in velocity of the fluid particles between the object and the fluid surface is confined to a region called a boundary layer. So, that is the definition. So, we can define the boundary layer as the region where the shear stresses are finite, and then the fluid particles between the object and fluid surface is confined to a region. The difference so you can see that if you consider a body like this, then you can see that this free stream flow is coming and the free stream velocity is coming like this. The streamlines are shown here, and then it is say this difference in velocity of the fluid particles between this object and the fluid surface is confined to a layer. This layer is called a boundary layer, and then you can see that here the shear stresses are finite, and then we can analyze with respect to this boundary layer, and then remaining fluid flow we can consider as a potential flow or ideal fluid flow depending upon the case. So, this way we can simplify the problem by considering the boundary layer and then the flow beyond the boundary layer. So, to say define various terms in boundary layer theory, let us consider free stream flow over a flat plate. So, here this case is the flow is taking place freely, and then we introduce a flat plate is introduced, so that say we can easily visualize how the boundary layer is generated, and then with respect to that we can define various parameters or various say aspects of boundary layer can be explained. So, here in this figure shows the boundary layer growth over a flat plate. So, here the flat plate is placed like this. So, here is the origin of the flat plate, so x is equal to 0 and the length of the flat plate is L, and then a free stream velocity or velocity, so u infinity, or here it is indicated as v infinity. This is the free stream velocity coming, and so it is touching on the flat plate placed on this. So, since now this flat plate, its velocity here on say here it is flat plate is not moving. So, obviously the say due to the no slip condition here where the fluid is touching on the surface of the flat plate, there the velocity should be 0. So, the velocity if we plot, you can see that from 0 it will be keep on increasing like this, and then we can identify a boundary layer like this. So, depending upon the case, here initially it will be laminar zone boundary layer, and then after sometimes turbulence starts and there is a transition zone, and then finally the boundary layer become turbulent, and then beyond this, as we discussed, it can be considered as a potential flow or ideal flow depending upon the problem. So, this figure shows the boundary layer growth over a flat plate. So, now this typical case we will be considering here to define various parameters. So, as we have already seen, as the fluid passes over the plate, the action of the viscous shear retards fluid, and the fluid such that the fluid velocity is say reduced in the lateral direction, and then the thickness of the boundary layer increases. So, due to the shear stresses, flow in the boundary layer is rotational and flow outside boundary layer is irrotational. So, here you can see that say here in the boundary layer region this flow is rotational, and then we can consider outside the boundary layer the flow is irrotational depending upon the case. So, due to shear stress, flow in the boundary layer is rotational and the flow outside the boundary layer is irrotational, and say from the as the fluid passes over the flat plate, then the boundary layer thickness is keep on increasing depending upon the problem. So, like this we can say define the various aspects of the boundary layer growth and how the system is behaving. So, at the beginning of the 20th century, the famous scientist Prandtl say tried to define say boundary layer, and then he tried to establish certain relationship so that various parameters like velocity and the pressure can be calculated with respect to the boundary layer. So, what Prandtl did is Prandtl considered the boundary layer as a surface dividing between the rotational and irrotational flow, just like in the case of a flow over a flat plate as we have already seen. He considered say this boundary layer as the layer which differentiates between the flow is whether it is rotational or irrotational. So, within the boundary layer, Prandtl considered the fluid flow as rotational, and behind or beyond the boundary layer he considered the flow as irrotational flow. So, here you can see say when a free stream velocity is coming over the flat plate, both sides it is shown. So, the boundary layer is developing, and then this is the rotational flow field within the boundary layer both sides of the plate, and beyond this it be Prandtl considered as irrotational flow. So, this is plotted for Reynolds number 10 at 10 how the fluid flow is behaving with respect to flow over a flat plate. So, now we will be defining various parameters of the boundary layer like boundary layer thickness and the displacement thickness, momentum thickness, energy thickness like that, so that we can differentiate various parameters with respect to the boundary layer, and further we can try to quantify, we can try to derive, or we can try to get an expression for the various parameters like velocity and pressure. So, say in the beginning of the 20th century when Prandtl considered this boundary layer theories, and then when he developed the boundary layer theory. So, as we have already seen, he differentiated the boundary layer between the rotational flow and the rotational flow, and when we can plot the velocity distribution. So, you can see that when the velocity, so due to the no slip condition at the bottom of the plate, that location the velocity is 0, and then it keeps out increasing. So, most of the definitions we can see the boundary layer, normal boundary layer thickness is generally defined as at that location where the say the 99% of the velocity of the stream flow, free stream velocity is achieved. So, the boundary layer thickness delta is defined as the small distance from the boundary where velocity attains a value which is very close, say about 99% to free stream velocity u infinity. So, if u infinity is the free stream velocity say at this location, so the boundary layer thickness delta is defined as this distance delta at which u by u infinity, that means the velocity at any location is u in the boundary layer, then u by u infinity is equal to 0.99, that distance is defined as the boundary layer thickness. So, through this we are just we are able to differentiate say whether the fluid flow is within the boundary layer or it is beyond the boundary layer. So, that location wherever the velocity within the boundary layer u by u infinity is 99% or u by u infinity is 0.99. So, that location is generally defined as the boundary layer thickness. So, depending upon various fluid parameters, flow parameters, this boundary layer thickness can vary. So, then say it depends upon many parameters like the fluid viscosity and the density of fluid and Reynolds number. So, the boundary layer thickness depends upon the many parameters, like if the Reynolds number is very high, then the boundary layer thickness may be much smaller. So, but anyway depending upon the fluid flow over say just like in the case of flat plate or other kinds of fluid flow. So, we have differentiated the boundary layer thickness as wherever the u by u infinity, that velocity ratio is equal to 0.99. So, this is the definition of the boundary layer thickness. So, boundary layer thickness, so as I mentioned, it is defined depending upon the velocity distribution. So, it is sometimes called the velocity thickness or the velocity boundary layer thickness. So, we have already seen with respect to the velocity only, we have defined the boundary layer thickness. So, sometimes due to this fact it is called a velocity thickness or the velocity boundary layer thickness. By a large number of experiments conducted in the controlled facility, Blasius has given an expression for boundary layer thickness for laminar flow case. For incompressible fluid flow or flat plate, he has shown that this delta by x. So, where delta is the boundary layer thickness, x is the distance from the beginning of the flat plate, delta by x he defined that he found is equal to 5 by square root of Rex, where Rex is the Reynolds number at that particular location. So, that means say here depending upon this say flow over a flat plate. So, at if this is x is the distance, say if x is the distance at which considered. So, if the flow is laminar, Blasius shown that is delta by x. So, delta is the boundary layer thickness, x is the distance from here. So, Blasius showed that this is equal to delta by x is equal to 5 by square root of Rex, where Rex is the Reynolds number at that particular location where we consider that section or to where we find the boundary layer thickness. So, like this for various problems, a large number of experiments conducted in the case of laminar flow and turbulent flow, a number of relationships are available in literature. So, now you have seen the boundary layer thickness, and next important definition in boundary layer theory is called displacement thickness. It is generally identified as delta star. So, the displacement thickness is defined as it is the distance measured perpendicular to the boundary by which the free stream is displaced to yield the same solution for flow outside the boundary layer as the boundary layer equations yield. So, due to the presence of the plate or presence of the solid, then in the say already a free stream velocity is there, and then the boundary layer is introduced, and then there will be shifting of the flow behavior. So, this displacement thickness is defined as the distance measured perpendicular to the boundary by which the stream is displaced to yield the same solution for outside the boundary layer. So, here it is shown like in this figure. So, if this is the boundary layer. So, this delta star is defined as this distance. So, that the distance by which it is shifted, so that the free stream is displaced to yield the same solution. So, that is defined as the displacement thickness. So, now If you consider this figure here, so this is the velocity variation with respect to flow over a flat plate. So u infinity is the free stream velocity and u by u infinity is plotted here, u versus within u versus y. So if b is the width of the flow section and a total volume rate of flow past a section delta, which we consider as the boundary layer thickness, then we can, with respect to this figure, we can write the discharge which is passing over, we can write as q is equal to b into integral 0 to infinity u dy, so that we can write as b into integral 0 to delta u dy plus b integral 0 to delta to infinity u infinity dy. So this will be the discharge which we consider over the flat plate case which we consider. So the total volume rate of flow that could have passed if there had been no boundary layer. So the first expression here is whenever there is boundary layer, so that is with respect to this velocity variation, since the presence of the solid, the velocity and the presence of the solid and the no slip condition, the velocity is reduced. So that velocity variation, the boundary layer is expressed as this u. So if there had been no boundary layer, then this same expression discharge we can write as this is equal to b into integral 0 to delta u infinity dy plus b into integral delta to infinity u infinity dy. So this one is with the boundary layer and the one is without the boundary layer. So with this we can see that reduction in flow rate by formation of the boundary layer is equal to qr is equal to qi minus q. So that we can write this is equal to b into integral 0 to delta u infinity dy minus b integral 0 to delta u dy. So that is equal to b integral 0 to delta u infinity minus u dy. So this is the reduction flow rate by the boundary layer formation. So now the displacement thickness we can write as the displacement thickness delta star representing a shift in free stream is obtained by equating this qr with the frictionless flow passing through an area b delta star. So with respect to this figure, this is delta star and b is the width of flow which we consider. So we got this reduction in flow. So this we can write as, we can equate this reduction of flow with respect to this displacement thickness b into delta star into u infinity is equal to b into integral 0 to delta u infinity minus u dy. So finally we can get an expression for the displacement thickness delta star as delta star is equal to 1 by u infinity integral 0 to delta u infinity minus u dy. So that is equal to integral 0 to delta 1 minus u by u infinity dy. So this is the expression for the displacement thickness. So this is actually an expression connecting with respect to the free stream velocity and the velocity in the boundary layer and the displacement thickness. So this difference in velocity of the free stream and the velocity in the boundary layer u infinity minus u is called the velocity deficit or velocity defect or velocity deficit with respect to the boundary layer formation. So the difference between the free stream velocity and the boundary layer velocity is called velocity deficit or the reduction in the velocity. So now we have first seen the boundary layer thickness and then the displacement thickness, and then you can see that say when we consider most of the fluid flow behavior, we will be dealing with the momentum and then we will be dealing with the energy. So what happens to the momentum when say in a free stream flow, if a flat plate is introduced or with respect to the formation of boundary layer, what happens to the momentum? So we can see that there will be also a change in momentum due to the formation of the boundary layer. So we can define an expression called momentum thickness here, and it is put as theta. So this momentum defined as the distance from actual boundary such that momentum flux through that distance at a velocity same as the momentum deficit due to boundary layer formation. So since the boundary layer is formed, then you can see that the velocity changes, and then there will be, when the velocity changes, momentum also changes. So there will be a deficit in momentum also with respect to the velocity change. So this momentum thickness we can define as the distance from actual boundary such that momentum flux through that distance at a velocity same as the momentum deficit due to the boundary layer formation. So if we consider the momentum, so since we have already seen most of the fluid flow is concerned, momentum is very important. So consideration of momentum is important in flow problems where pressure and shear forces are involved. So we can see that in the case of viscous flow, this shear force we are considering. So this momentum is very important. So we will derive an expression here for momentum thickness. So actually the expression is written as theta is equal to u by u infinity integral 0 to delta 1 minus u by u infinity dy. So this also we can derive as in the earlier case where we discussed the displacement thickness. So here with respect to the flow over a flat plate, which we have seen earlier. So say if the width of the fluid flow which we consider is b, then the momentum transport in the boundary layer we can write as b into integral 0 to delta rho u dy into u, where delta is the boundary layer thickness, u is the velocity in the boundary layer, and rho is the density of fluid flow. So that is equal to b into integral 0 to delta rho u square dy. So now momentum for the same mass of flow when we consider the u infinity, that means the free stream velocity. So with respect to the free stream velocity, we can consider this is equal to b into integral 0 to delta rho u dy u infinity. So now if you consider between these two expressions, you can see that there will be a momentum defect or reduction in momentum. So that we can write as momentum defect or deficit, we can write as b into integral 0 to delta rho u infinity minus u dy. So we consider the momentum with respect to if there is no boundary layer, this expression, and if there is boundary layer, then this expression. So the momentum defect or momentum deficit we can write as b into integral 0 delta rho u infinity minus u dy, and then we have defined momentum thickness theta. So if theta is the momentum thickness, then momentum transport through area b into theta can be written as rho b theta u infinity square. So that we can equate with respect to this momentum defect derived here, that is equal to b into integral 0 to delta rho u infinity minus u dy. So here from with this we can get an expression which we have already seen in the last slide. So we can get theta is equal to, as we have already seen here, theta is equal to, from the earlier derived expression from this relation, we get theta is equal to u by u infinity integral 0 to delta and 1 minus u by u infinity dy. So this is the expression for the momentum thickness which we can derive from this expression. So like this, say we can derive the expression for the momentum thickness. And so for flow past a flat plate, so we have seen the typical case of for flow past a flat plate. So in this case, if we consider the displacement thickness delta star and momentum thickness theta, then experimentally, or say we can show this for various cases, this delta, the boundary layer thickness, is equal to 3 times delta star the displacement thickness, that is equal to 7.5 times the momentum thickness which we have considered. So for flow past a flat plate, we can show that delta is equal to 3 times delta star is equal to 7.5 times theta, and then also one factor called shape factor, in general defined literature, h is equal to delta star by theta. That means the ratio of the displacement thickness to momentum thickness is defined as the shape factor. So if you plot with respect to, if you in the plot of the velocity variation with respect to depth, boundary layer depth y, we can plot this theta here, theta, then delta star, and then this is the delta, the boundary layer thickness, this is displacement thickness, this is a momentum thickness. So relative magnitude of the magnitudes of the delta star and theta are plotted here for a flow over a flat plate. So this is about the parameters of momentum thickness or displacement thickness and the boundary layer thickness delta. So and another important aspect is the what happens whenever in a free stream flow we introduce a flat plate, and then what happens to the energy variations with respect to the boundary layer formation. So there with respect to this we can define a term called energy thickness delta E. So here the energy thickness delta E is the thickness of a layer of fluid moving with a velocity u infinity that represents the loss of energy transport rate. So this is the definition of the energy thickness delta E. It is thickness of layer fluid moving with a velocity u infinity that represents the loss of energy transport rate. So decrease in energy transport rate caused by the boundary friction, we can write as, say if we consider a fluid width as b, so half b integral 0 to delta rho u infinity square minus u square dy. So if delta E is the energy thickness, then the energy transport through the flow area b into delta E referred to the free stream velocity u infinity is half rho b delta E u infinity cube. So, this is the with respect to the energy thickness for the flow through a area B delta E. So, now we can equate this to the earlier expression, this one and this one here. So, that we can write as half rho B delta E u infinity cube is equal to half B integral 0 to delta rho u infinity square minus u square dy. So, finally, we can get an expression for the energy thickness as delta E is equal to integral 0 to delta u by u infinity 1 minus u square by u infinity square dy. So, this is defined as the energy thickness, and also we can calculate the energy loss per unit time as EL is equal to half b rho b delta E u infinity cube. So, this is the energy loss per unit time, and the energy thickness delta E is defined here. So, these are some of the important parameters in the boundary layer flow, which we will be considering while estimating various other parameters like velocity, pressure or shear stress in the boundary layer. So, the important parameters, 4 parameters we have seen. One is the boundary layer thickness, second one is the displacement thickness, third one is momentum thickness, and fourth one is the energy thickness with respect to the boundary layer formation. So, before going further, we will just briefly discuss a small example where we will check how the variation of this displacement thickness, energy thickness and momentum thickness takes place with respect to the boundary layer thickness. So, here we consider a small example problem. Assume the velocity distribution in the boundary layer is given by u by u infinity is equal to y by delta to the power 1 by 7. We have to calculate the ratio of displacement thickness to boundary layer thickness delta star by delta, and momentum thickness to delta, and energy thickness delta E to delta, and also if at a certain section the free stream velocity observed to be 12 meter per second and thickness of boundary layer as 2.5 centimeter, then calculate the energy loss per unit length by taking the density of air as rho is equal to 1.226 kilogram per meter cube. So, an expression for the ratio of the velocity in the boundary layer with respect to the free stream is given, and with respect to that we have to find out the ratio between the displacement thickness to boundary layer thickness and momentum thickness to boundary layer thickness and the energy thickness to the boundary layer thickness. So, here the solution is simple, since we have already derived various expression for the displacement thickness, moment thickness and energy thickness. So, and we have already given the ratio between the velocity in the boundary layer to the free stream velocity u by u infinity. So, we can just substitute in the various relationship. So, here the displacement thickness delta star is equal to integral 0 to delta 1 minus u by u infinity dy, that is equal to integral 0 to delta 1 minus y by delta to the power 1 by 7 to dy. So, this is after substituting for this u by u infinity is equal to y by delta to the power 1 by 7. So, this we can approximate, and then we can show that this delta star, the displacement thickness is equal to delta by 8, so that we can write the ratio between the displacement thickness to boundary layer thickness delta star by delta is equal to 0.125. So, similarly we can write for the momentum thickness. So, theta is equal to integral 0 to delta u by u infinity 1 minus u by u infinity dy. So, this is ratio is given as y by delta to the power 1 by 7. So, we can just substitute here, that is equal to integral 0 to delta y by delta to the power 1 by 7 1 minus y by delta to the power 1 by 7 dy. So, this we can show that theta is equal to 7 by 72 delta, or theta by delta it is equal to 0.097, and then the energy thickness is concerned, again we can substitute for the expression which we have derived. So, delta E is equal to integral 0 to delta u by u infinity into 1 minus u square by u infinity square dy. So, that is equal to integral 0 to delta y by delta to the power 1 by 7 into 1 minus y by delta to the power 2 by 7 dy. So, that we can show delta is equal to 7 by 40 delta, or delta E by delta energy thickness ratio with respect to the boundary layer thickness is equal to 0.175. So, now the energy loss per unit length per unit time can be obtained as EL is equal to half rho delta E U infinity square. So, delta E is, we can substitute as 0.175 into 2.5 centimeter, where delta is 2.5 for the given section. So, this is equal to 0.4375 centimeter. So, from which the free stream velocity is already given as 12 meter per second. So, we can calculate this EL, the energy loss per unit length is equal to 4.63 joules. So, like this we can calculate various parameters. So, we have already seen the fundamental definitions with respect to the boundary layer as boundary layer thickness, displacement thickness, momentum thickness and energy thickness. So, these parameters we can use to determine other parameters like velocity, shear or other expressions. So, now we have defined what is a boundary layer, and then we have seen the various concepts behind the boundary layer theories, and now say we have also seen with respect to say the flow over a flat plate. We have seen, say, initially the boundary layer is laminar, and then a transition takes place as the boundary layer grows, and then a turbulent boundary layer is generated. So, now after with respect to the fundamental concepts of the boundary layer we have seen, now we will see the laminar boundary layer and then the turbulent boundary layer. So, now initially we will discuss this to differentiate between the laminar and turbulent boundary layer. We will see the flow over a flat plate again. So, here in this figure, so you can see that this is the free stream velocity coming, and then we introduce a flat plate like this. So, if you plot the velocity profile for laminar and turbulent boundary layers, we can see that. So, here the boundary layer, so with respect to boundary layer thickness, we have already shown in the previous figure for a flow or a flat plate how the boundary layer is generated. So, you can see that initially it is now up to this location it is free stream velocity, and then the boundary layer is generated. So, initial distance, for some distance you can see that the flow is totally laminar, the flow in the boundary layer is totally laminar in nature, and then again after some time a mixing starts, and then a transition state takes place, and finally you can see that the flow become turbulent after a distance. So, in the same for the flow over a flat plate we can see that a laminar boundary layer, then a transition and the turbulent boundary layer. So, within this boundary layer you can see that the flow takes in layers. So, in the case of laminar boundary layer, here you can see for laminar boundary layer, within this boundary layer the flow takes place in layers, each layer gliding over the adjacent layers. So, initially when for the flow or flat plate, initially if you measure or if you observe the laboratory, you can see that flow is in layers and gliding over the adjacent layers. So, that is why we can say that area of as laminar boundary layer. So, here with respect to the laminar flow theories which we have already seen, which we have discussed earlier, the exchange of mass or momentum takes place only between the adjacent layers on a microscopic scale. You can see that between the layers only the mass or momentum exchange takes place, and then you can see that the dynamic viscosity of coefficient is used to predict the shear stress within the layer. So, and for this here this mu or the dynamic viscosity coefficient is used to predict the shear stress, and it is found only where the flow is taking place with a small Reynolds number. So, after say when we in the free stream velocity, when we say for example, here is the free stream velocity is coming like this, and then we introduce the flat plate like this, and then you can see that here say initially some region the Reynolds number will be low, and then at that location only the flow will be laminar, and then the say when the Reynolds number increases the flow may become obviously turbulent. So, the initial stages of the boundary layer development exhibits characteristic of the laminar motion. And then if you define the Reynolds number with the boundary layer at a distance x as Rex is equal to u infinity into x by nu. So, u infinity is the free stream velocity, x is the distance which we consider here, and nu is the kinematic viscosity coefficient. So, with respect to the Reynolds number, we can say the boundary layer keeps on growing, and then with respect to the, if you at different locations, if you show the boundary layer, if you plot the boundary layer, you can see that say as we have already seen in the earlier figure. So, here is the plate, flat plate which we introduced, and this is the free stream velocity which is u infinity, and then when it hits you can see that a boundary layer is generated, and then after some time it becomes say transition stage, and finally it becomes turbulent. So, this region where it is laminar. So, here say at this location, various location we can say x we can define this Reynolds number Rex as u infinity into x by kinematic viscosity nu. So, if you define x from here at various location, we can define the Reynolds number, and then with respect to this we can identify where the transition starts from laminar to turbulent. So, now say with respect to this, for it, say if we consider the 2D laminar boundary layer, it can be shown that referring to the figure below. So, here the boundary layer thickness, say this is the leading edge and this is the flow in this direction. So, the laminar region of the boundary layer. So, if delta is the thickness of the boundary layer at a distance x from the leading edge, then you can show that delta by x is equal to phi into square root of nu by u infinity into x. So, that is equal to phi by square root of Rex, the Reynolds number at that particular location. So, that we can write delta is equal to phi into square root of nu into x by u infinity. So, here as we have already shown here in this figure, say at various locations this boundary layer for this laminar region, say if this is the x at this distance. So, delta we can define as phi into square root of nu into x by u infinity, which is the free stream velocity, and x is at a various location which we consider. So, this relationship derived by Blasius through various experiments we can utilize, and then if you define a critical Reynolds number from which onwards the flow is transition or turbulent, then we can put that condition. So, the boundary layer thickness delta. So, with respect to the figure here, as we have already shown here. So, this figure we can say with respect to the boundary layer various characteristics for this laminar boundary layer, we can get various characteristics. So, the various characteristics are defined here. The boundary layer thickness delta decreases with increasing Reynolds number. So, you can see that this boundary layer thickness, same as I mentioned, when the flow velocity is very large, then the Reynolds number is keep on same is increasing. Then when the Reynolds number is increasing, the boundary layer thickness, the thickness of the boundary layer reduces, and then it is confining near to the very near to the solid surface. So, one of the important observation we can see the boundary layer thickness, say the formation of the boundary layer when we discuss the formation of the boundary layer. So, with depending upon the Reynolds number, if the Reynolds number is very large, then a small boundary layer will be formed, and same when it say the thickness of the boundary layer decreases with the increasing Reynolds number. And then for high velocity flow the boundary layer will be very thin. So, the Reynolds number increases with respect to the flow velocity. So, we can say that when the velocity is very high, we will be having a thin boundary layer. And then another important observation is for ideal flow, the Reynolds number tends to infinity, so boundary layer thickness vanishes. So, we have already seen earlier. So, the case of if you consider say the real fluid to ideal fluid, so that the Reynolds number in the case of ideal fluid it tends to infinity and boundary layer finally vanishes. So, that is what we observe in the case for ideal fluid there is no boundary layer. So, and then for a given fluid flowing at a certain free stream velocity, the boundary layer thickness increases with increasing x. So, that is what we have seen here. So, when the distance is increasing from this point to this point, the boundary layer thickness is keep on increasing. So, this is for a given fluid flow condition. When we introduce a flat plate in a free stream velocity, then from starting from the leading edge of the plate, then this is the trailing edge. So, from here onwards, the boundary layer thickness is keep on increasing. So, this is for a given fluid flowing at a certain free stream velocity, the boundary layer thickness is increasing with increasing x, and then boundary layer thickness increases with increasing kinematic viscosity nu of the fluid. So, we have already seen with respect to the previous expression, delta is equal to phi into square root of nu x by u infinity in the case of a laminar boundary layer. So, from that we can see that the boundary layer thickness increases with increasing kinematic viscosity nu of the fluid. So, from this say we can see that we can finally summarize that say depending upon the as far as boundary layer formation is concerned. So, the boundary layer thickness or the how much is the boundary layer effects to be considered depends upon the kinematic viscosity, and then depends upon the shape of the body over which the flow is taking place, and then the Reynolds number or the fluid flow velocity. So, depending upon all these parameters, the nature of the boundary layer changes, and then we have to consider the boundary layer accordingly for various solutions. So, now we have already discussed here the fundamental concepts behind the boundary layer, and then how a boundary layer is developing with respect to flow over a flat plate, and also we have seen various definitions with respect to the boundary layer, and also we have seen say how the boundary layer variations takes place with respect to laminar flow or the laminar boundary layer. So, further we will be discussing the various aspects of turbine boundary layer, and then we will be trying to get various expression for velocity, shear, etc. in the next lecture.